Hello students, welcome you to another new video from our electromagnetic theory chapter. Today we will discuss about all the Maxwell's equations and their corresponding derivations, both in integral form as well as in the differential form. Already we have discussed about what is del operator, different operations of del operator over any scalar quantity as well as over any vector quantity. Then also we discussed about all the fundamental laws or basic laws of electrostatic and magnetostatic which are used in electromagnetic waves as well as electromagnetic theory. Now we will discuss about the Maxwell's equations. So let's start the lecture. Then what are Maxwell's equations? First we will discuss. Maxwell's equations are nothing but Gauss law in electrostatic, that is also said to be Maxwell's equation, which is equal to the electric flux equal to Q by epsilon naught, or you can write E dot ds integration over S equal to Q by epsilon naught. This is one theorem. Then second one is Gauss law in magnetism, which is equal to magnetic flux 0, which states that is integration over S B dot ds equal to 0. Third one is Faraday's laws of electromagnetic induction. So Faraday's laws of electromagnetic induction is EMF equal to minus d phi b by dt. And fourth one is modification of Ampere's law by Maxwell, that is the modified Ampere's circuital law. The modified form is B dot dl integration over C or L equal to mu naught I plus ID. These are the four basic laws already we have studied in the last lecture, and these four laws are said to be the Maxwell's equation. So first we will discuss what are the integral forms. Integral form means when the equation contains integration, that is said to be integral form. Then the differential form. But the differential form here we are going to find out by using del operator, and we are going to derive each one of them. So first we will write the integral form. So here from this equation also you can identify the integral form. In integral form, first one is E dot ds Gauss law in electrostatic equal to Q by epsilon naught, or you can also write down like epsilon naught E dot ds integration over S equal to Q. See, epsilon naught is there, divided, we have divided, we can multiply to this side. Epsilon naught E is said to be capital D. This is said to be integration over d dot ds. D dot ds equal to Q, or here also in terms of volume charge density you can write down integration over S d dot ds equal to integration of V over dV. Okay, where d is epsilon naught E. This is a vector quantity which is known as electric displacement vector. So this is integral form of the first equation, which is said to be Gauss law in electrostatic. Similarly, Gauss law in magnetism also we can write. In next page we can write Gauss law in magnetism. The second equation, Gauss law in magnetism is directly B dot ds. Already it is in integral form equal to 0. Clear? Then third equation we can write EMF equal to minus d phi b by dt. This is the original equation. Faraday's laws of electromagnetic induction, and negative sign is from Lenz's law, that means both induced EMF and flux change are opposite to each other. In case of EMF is nothing but the maximum potential. So we can write down in terms of relation between EMF and electric field. That relation is integration E dot dl integration over C or L equal to minus del by del t, partial derivative we can also write. Phi is nothing but flux, this is magnetic flux, so dot product of field and area integration over S. Clear? This is the third equation. Then the fourth equation, already we know that the modified Maxwell's modification of Ampere-Circuit law, that is B dot dl. B dot dl integration over C equal to mu naught I plus ID. This is the original equation. Now on right hand side we can convert from current to current density. Remember current density? Current J vector, which is equal to I by A, current by area. So by using that we can write down integration over C B dot dl equal to mu naught J dot ds and integration jd dot ds. This is integration over S, integration over S. See how I have changed that. I current equal to current density equal to J equal to I by A, I equal to J dot A, because J is a vector quantity, area is a vector quantity, current is a scalar quantity. So dot product of current density and area gives us the current. I is always equal to J dot A, dot product. So I equal to J dot A, area, so small area ds, total integration we can take. Similarly ID will be JD dot A, its current density, that is displacement current density, and area. So these are the integral form. We can also change the integral form by different method, by changing that JD in terms of displacement vector capital D also we can change. Now we can take the differential form. Then we will discuss about what are the differential form. The differential forms are, the first equation you can see, it is d dot ds equal to rho dv. The differential forms are, the first equation is del dot d equal to rho. The second one is del dot b equal to 0. Third equation is del cross E equal to minus del B by del T. And the fourth equation is del cross B equal to mu naught J plus del D by del T. We will derive each one of the differential equations. So the differential equations are del dot D equal to rho, second one is del dot B equal to 0, del cross E equal to minus del B by del T, and del cross B equal to mu naught J plus del D by del T, where D is electric displacement vector. So now we are going to derive the equation 1. Equation 1 is del dot D equal to rho, its derivation. So we will derive from the basic equations. Okay, from integral from Gauss law. From Gauss law we know that flux equal to Q by epsilon naught. Again flux is nothing but integration over S E dot ds dot ds equal to Q by epsilon naught. Again, if rho is charge density, then we can write down Q equal to rho dV. Already we know that volume charge density. If we use that, then we will have E dot ds integration over S equal to integration of V rho dV, and here 1 by epsilon naught. 1 by epsilon naught. Now we can take epsilon naught to this side. Clear? So if we take epsilon naught to this side, this will be integration over S epsilon naught E dot ds equal to integration of V rho dV. This is similar to that of that Poisson's equation, and epsilon naught is capital D, so integration over S d dot ds equal to integration of V rho dV. We used here the formula that D equal to epsilon naught E. We use this formula. Okay, clear? We get this equation. Now you can see on left hand side we have surface integral, on right hand side we have volume integral. We are going to use Gauss divergence theorem to convert from surface to volume integral. If we use Gauss divergence theorem, if we use to the LHS, this side, D dot ds will be del dot d dv. So this will be del dot d dv integration over v equal to, here also integration v rho dv. Clear? Closed circuit you can give or you can omit. Now you can see we have derivative, we have integration over v on both sides. We can take to one side. So this is del dot d minus rho integration over v dv equal to 0. Again, as we know that integration of a quantity never be 0. Only possibility is that that quantity is 0. So del dot d minus rho equal to 0 or del dot d equal to rho. This is the simplest derivation. Okay, you can easily do this one. Already you have done this one in Poisson's equation. Okay, so this is the derivation of first equation, del dot d equal to rho. Now we will go to second equation. Second equation is again the easiest one. Second equation is del dot b equal to 0. Now we will derive. From Gauss law in magnetism, we know that magnetic flux equal to 0. So magnetic flux, as we know that flux is nothing but dot product of field and area, we can directly write down this is b dot ds integration over s equal to 0. Now directly we can use Gauss divergence theorem. Gauss divergence theorem, if we use, we can convert from surface to volume. So surface to volume will be, as we know that a dot ds equal to div a dv. Similarly, b dot ds will be div b dv. So del dot b dv integration over v equal to 0. And integration of a quantity 0 means same thing. The quantity is 0. That means del dot b equal to 0. So this is the derivation of second equation. We have derived first equation, we have derived second equation. Third equation we will derive from the Faraday's laws of electromagnetic induction. So from Faraday's law, third equation is del cross E equal to minus del V by del T. We have to derive this one. So third equation we will derive from the Faraday's laws of electromagnetic induction. So from Faraday's laws of electromagnetic induction, we know that E equal to minus d phi b by dt. EMF equal to negative rate of change of magnetic flux linked with the coil minus d phi by dt. Now we know that the relation between electric field and EMF, electric field and EMF equal to E dot dl integration over C or integration over L. Again, magnetic flux we can write down flux is B dot ds. Since it is magnetic field, we can use B. We can use both of them in equation number 1. If we use them in equation 1, on left hand side we will have E dot dl integration over C equal to, on right hand side, del by del t of phi b is integration over s b dot ds, or on right hand side, left hand side we can remain same, C E dot dl remains same. Here minus s integration over s del b by del t dot ds. Now see equation number 2. On LHS we have integration over C, line integral. On RHS, we have integration over S. So here, in order to convert both side to either surface or both side to either line integral, we have to use Stokes theorem. So Stokes theorem was A dot dl equal to del cross A ds. You remember this one or not? Integration over S and integration over C. This is Stokes theorem. Now we have to use this Stokes theorem. We have to use here to LHS. If we convert the LHS from line integral to surface integral, then you can equate the both sides. So if we use this one, then the LHS of this equation will be integration over C. Here you can see A dot dl, here we have E dot dl. So this will be converted to, directly I am writing E dot dl. LHS was E dot dl. This will be converted to integration over S del cross E dot ds. This is a conversion. Only in place of A we have changed to E, because in our equation we have E. Now we have to use this equation in equation of LHS of equation number 2. So del cross E dot ds. So del cross E dot ds integration over S. On the right hand side you have minus integration over S del b by del t dot ds. Now we can take, since both sides are surface integral, we can take both side to one side, both of them, then we can rearrange. Once we rearrange, it will be del cross E minus on left hand side it will be plus del b by del t dot ds equal to 0. And since integration of a quantity, integration never be 0. Since integration never be 0, this quantity is 0. So quantity 0 means del cross E plus del b by del t equal to 0. And A plus B 0 means obviously we know that A equal to minus B. So del cross E equal to minus del b by del t. So now we have proved equation number 3 also. Third Maxwell's equations. Already we have proved. Next we will go to the fourth one. So the fourth equation from Maxwell's modified Ampere circuital law we have to derive. So equation we have to derive is del cross B equal to mu naught J plus del d by del t. We have to prove this one. The fourth equation we have to prove from modified Ampere circuital law. Now we have B dot dl integration over C equal to mu naught I plus id. This is the equation. But if J vector and JD vector are current density of conventional current and displacement current. Conventional current, that is a normal current, and displacement current. Then we can write I equal to J dot A, or in terms of small area you can directly write down J dot ds integration over S. Similarly, ID equal to, you can directly write down integration over S JD dot ds. J is current density, JD is displacement current density, and current density is nothing but the amount of current flowing per unit area, and current equal to always dot product of current density and area. We have to use I and ID in equation number 1. Equation 1. So the right hand side will be converted into surface integral. So you can write the right hand side, left hand side remains same. that is B dot dl integration over C. On the right hand side we have mu naught. If we take integration common, then J plus JD, or if you get confused, let me write first the entire term, then you can take common. Mu naught integration over J dot ds plus integration over S JD dot ds. See here, we just use in place of I and ID, we use the integral term. Now our aim is to convert that equation to this format. So we can use Stokes theorem, because here you can see surface integral, line integral. Clear? Surface integral, line integral, all these are there. So we can use, if we use Stokes theorem, to LHS of above equation, then we can write LHS of above equation, B dot TL. This was the LHS integration of C. This will be del cross B dot ds. Del cross B dot ds integration over S. Now, if we use this one here, this will be converted to surface integral. So we get the answer like integration over S. We have to use this here. Instead of B dot dl, we can directly write down this one. Del cross B dot ds equal to, on the right hand side we can take mu naught integration over S J plus JD dot ds. Sure, here you can see on left hand side we have surface integral, on right hand side also we have surface integral. We can take them to one side and then we can rearrange. So if we rearrange, this will be like del cross B, directly I am writing mu naught J plus JT, because here you can see surface integral, here surface integral, we can take left hand side, integration of that term is 0, because integration never be 0, so del cross B equal to mu naught into J plus JT. But this is not our required result. In our required result, instead of JD, it was given del D by del T. So now we have to convert. Let's give it equation number 3. We have to convert. JD. JD is displacement current density. So displacement current density means displacement current divided by area. And displacement current formula is epsilon naught A del E by del T, and here divided by area. Displacement current formula, this one, epsilon naught A del E by del T. Now we can cancel area, so remaining part will be epsilon naught del E by del T. If we take, since epsilon naught is a constant quantity, we can take inside the derivative term, so this will be del by del T of epsilon naught E, but epsilon naught E is capital D, so we can directly write down del D by del T. Okay, so we get JD is nothing but del D by del T. Now we get our required solution, JD equal to del D by del T, so we can write down del cross B equal to mu naught J plus del D by del T, where D is electric displacement vector, mu is permeability of free space, J is conventional current density vector, B is magnetic field induction. So this is the proof of fourth Maxwell's equation for electromagnetic theory. Clear? So practice all these equations. All these equations are very much important for electromagnetic theory chapter, and this type of question you may get for derivations, okay, in exam. Thank you.